Alright, day 8 of Advent of Code. Today's problem, we have the top treehouse. This is our first 2D grid problem of this cycle of Advent of Code. Luckily, I happen to have a 2D grid parser lying around from last year. That was very convenient here. We're parsing it into grid 2. This is actually an array type. For this particular problem, it turns out we don't need to mutate any of the values within this grid. So array is what we want rather than hash map. But so parsing this is going to be easy. Now we have to think about the problem. The problem here is that each of these numbers represents the height of a tree in this sort of rectangle or square clump. And for the first part of the problem, we want to determine how many of these trees are visible from the outside. So we can look, we can look from the left along this way. We can look from the right along this way. We can also go from the top, or we can look from the bottom. And basically, once a tree is obstructed by a taller tree, then we are not able to see it from any of those angles. So for instance, this 4 is one of the few examples in this grid that is not visible from the outside, because this 9 occludes it, this 9 occludes it, the 5 occludes it from this side, and the 7 occludes it from on top. So the 4 is not visible. On the other hand, this 5 is visible, because we can see over this 3 to see the 5. This 3 is actually occluded, because it's occluded from this side by the 3 and the 5, and the 5's on the other side. So that's the first part of the problem. The second part of the problem is that we're going to assess the Scenic score or something like that for each of the items in the tree, and that will depend how many trees are visible in each of the 4 directions. And that's basically a matter of looking and saying, okay, so we're at a tree of level 5. How far can we go until we see another tree that is 5 or taller? So, for instance, we can go 2 in this direction to get a tree of 5, 2 in this direction to the edge, only 1 in this direction, and then 1 in this direction, and we just multiply those to get the score. So, there's nothing too clever with the algorithms I wrote here. It's more or less just sort of brute force looping through these items. But let's just go ahead and see what that code looks like. As I said, we're just parsing the 2-digit array using this utility, so the input part is easy. So for the first part, the easy solution, what are we doing? So we have to count in all 4 of the directions. So I broke this up into 2 helper functions. One of them is counting visible in a horizontal sense, and one of them is in a vertical sense. So this function, count visible horizontal, it takes our grid, it takes a list of the different columns that we want to assess, because we're looking at it horizontally, and so we want a list of all the indices of the columns. And so this could be in the ascending order, or could be in descending order. That's basically the difference between counting visible horizontal from the left versus the right. And all we're doing is basically doing a fold over a set. So the set is just the coordinates, all the coordinates that are visible, and we're just going to accumulate the set over all of these different visibility functions. So we want to avoid duplicates, that's why we're using a set. And within this function, again, we're just folding over this coordinate. We're also folding, though, over the highest, the maximum height that we've seen going along. And so the way this works is we look at the next height in, we're looping through all of the columns in this column, and we get the height at this row and the column. And if it's greater than the previous height we've seen, has to be strictly greater, then we will insert this particular item into our set. We can see it from the outside, and we're going to reassign next height based on the item here. Otherwise, nothing changes. The highest seen is still our highest seen, and we don't add anything new to our set. So the only thing that changes with count visible vertical really is that we're taking the rows as our input instead of the list of columns, and we're pegging it to a single row in the first one and then a single column in the second function. So then all we really need to do, we do the fold counting horizontally with the normal list of columns. So this is, let me think, count visible horizontal with columns goes from the left. That's this first row, so looking at the left. Second row, we reverse it, so we're actually looking from the right. And then count visible vertical So going from the top, I think, probably. Yes, we are counting from the top, seeing how many trees are visible from the top, and then the fourth line is how many are visible looking up from the bottom. And we just fold all those together and we take the set size, and that gives us our answer. Nothing, no more post-processing that we have to do with that answer. So we can move on to the second part of the problem. And this is basically a matter, we just loop through all of the indices in our tree grid, and we apply this function where we're looking for the score at that particular index. This is just a matter, we look up, we look left, we look down, we look right. So we look in all four directions and we multiply those scores together. And each of these is just basically it's a loop. What we're doing here is a take while. So we're looking in the direction and we are counting the number of trees as long as the height of that tree is strictly less than the height here, the height at this particular row and column. And because that will allow us to add 1 to the score in that direction. There's some extra logic we have to add, like, okay, if we're at the top, our score is going to be 0 no matter what. We actually, the way I form this range, it would actually be invalid, so I need the special case. And then similarly, we also need a special case on, if we reach the end, if we look up and we reach the top, then we can just return the values we got from the list, the number of values. Otherwise, we have to add 1 because we have to include the tree that we didn't take. It's a little convoluted. There might be a simpler way to write this up, but I don't know. I didn't feel like investigating too much more because this just seemed to work, and we apply the same pattern just in the other 4 directions. Everything that's different here is we're just we're swapping rows and columns, and we're just doing we're doing just enough things differently that I didn't feel like looking at how to refactor these. There might be a way to make this look nicer, but it's it works. It functions. So we assess the Scenic score. We take the maximum. That's our solution. And there's nothing more to it than that. So I wrote, again, some tests, and all the tests are passing for day 8. Let me open up, see what this looks like. So these are the values we get. So our final Scenic score, 392,000 in the middle of this very large forest of trees. So these are the heights I got. But that's all for our day 8 solution. Come back again tomorrow, and hopefully, if I'm on time and able to do these videos, then I'll have the day 9 solution up tomorrow. So thank you so much for watching, and make sure to subscribe to our channel and to the Monday Morning Haskell mailing list using that subscribe link in the video description. Thank you for watching.